Welcome back to the deep dive. Today, we're looking at water, H2O, but really pushing it to its limits. We're talking about superheated water. You might hear it called subcritical water or maybe pressurized hot water.
That's right. And it's quite specific, actually. We mean liquid water, but under significant pressure. And it's hot, somewhere between the normal boiling point, 100 Celsius, and its critical temperature, which is way up at 374 Celsius. That pressure is absolutely key. It's what forces the water to stay liquid. And that's where things get really interesting chemically.
Yeah, the source material kept mentioning anomalous behavior. What exactly is going on there? What's changing when you force water to stay liquid past boiling?
Well, it really comes down to the hydrogen bonds, those connections holding water molecules together.
Right, the ones that make water so unique.
Exactly. As you heat water up into this superheated range under pressure, those bonds start to break down quite significantly.
Right.
And because of that, the water becomes, well, much less polar.
Less polar. So it stops acting like the water we know, the one that dissolves salt and sugar so well.
Precisely. We can measure this using something called the dielectric constant. It's basically a measure of polarity. For normal water, it's about 80. But at 2.5 degrees Celsius, it drops right down to about 33.
33. Okay, and what does that number mean in context?
Well, 33 is actually the same polarity, the same relative permittivity as methanol.
Methanol, an organic solvent. So wait, why is water acting like an organic solvent such a big deal?
Because suddenly you can use just plain hot water, well, pressurized hot water, to dissolve things like oils, greases, organic compounds that are normally completely insoluble in regular water. Think about replacing, nasty petroleum-based solvents with just water.
Okay, that's huge.
And there's more. It's not just polarity. The self-ionization of water also ramps up dramatically. Remember pKw? Normally 14 at room temp?
Yeah, neutral water.
Right. Well, at 250 degrees Celsius, it drops closer to 11, which sounds strange, but it means the water is acting like a much stronger acid and a much stronger base, all at the same time. It's chemically ambidextrous, you could say.
Wow, okay. Stronger acid, stronger base, and less polar. That must open up a lot of possibilities for, say, extraction, getting things out of materials.
Oh, absolutely. The solubility changes are staggering. For many organic materials and even gases, solubility can increase by several orders of magnitude.
Orders of magnitude, like how much?
Take PAH's polycyclic aromatic hydrocarbons. Nasty stuff. Their solubility can jump by, get this, 5 orders of magnitude. That's 100,000 times between 25 and 225 Celsius.
Incredible. Are people actually using this?
They are, commercially too.
Yeah.
For instance, extracting specific starch compounds from marshmallow-root, stuff used in skincare products. It's much cleaner than using chemical solvents.
Right, cleaner. And that brings us to chemical reactions. It sounds like superheated water isn't just dissolving things, it's actively participating, maybe as a catalyst too.
Yes, exactly. It can act as the solvent, certainly, but also as a reactant itself, and even catalyze reactions. This is really promising for green chemistry. Think about processing organic waste or biomass. There are processes like thermal conversion, TCC I think it's called. They use superheated water around 250 Celsius. They can take something like turkey processing waste and convert it relatively quickly into a light fuel oil.
Like a biofuel.
Essentially, yes. And there's another one, the slurry carb process. It uses similar hydrothermal tech to take wet, solid bio-waste and turn it into a stable, dryish, solid fuel. Again, no harsh chemicals needed, just hot, pressurized water.
Okay, but let's talk energy. It must take a fair bit of energy to heat water that hot and keep it under pressure, right?
Right.
Is it actually efficient compared to, say, boiling it off?
That's a fair question. But yes, the sources suggest it is quite efficient, relatively speaking. Heating liquid water up to, say, 250 degrees Celsius at 5 megapascals, pressure takes about 976 kilojoules per kilogram. That sounds like a lot, but compare it to the energy needed to actually vaporize water for something like steam distillation. That takes way more energy because of the phase change. So thermodynamically, keeping it liquid is often better.
Okay, so it's effective, it's potentially greener, it's relatively efficient. What's the catch? There's always a catch.
There is, and it's a big one. Corrosion. Superheated water, especially if there are salts or acids dissolved in it, can be incredibly corrosive to metals, like really aggressive.
Ah, so the equipment itself is a challenge.
Definitely.
Yeah.
Especially once you get above, say, 300 degrees Celsius. You often need specialized and usually expensive corrosion-resistant alloys to build the reactors and pipes. That's a major practical hurdle for widespread use.
Right. So let's wrap up with this thought then. We've seen how effective superheated water can be, how it acts like this amazing tunable solvent replacing toxic chemicals. It and it's a big if we could universally solve those really tough corrosion challenges, make the equipment cheaper and more robust. What kind of new green chemistry, what new applications might we unlock? Something for you to think about. We'll see you next time on The Deep Dive.